Hi, everyone. We're on to section 11.5. So we're going to be talking about lines, planes embedded within three-dimensional space. And we have 11 examples to get through today. So we're going to get right into it. The first one we're looking at is construct position vectors, describing the points, making up the line L passing through point A and B. So generally what we're trying to do is make the line, and we've done this before actually. To quickly review how to do that, what I'd like to do through this, we're going to get a bunch of different examples, right? So what I'd like to do is plan ahead and try to make a game plan, then execute that for each one of these different situations. So here we're given 2 points. We should make a direction vector according to those 2 points, because that gives us the direction of the line that we want to go through. So make direction vector using A and B, and then write it in parametric vector form. When they say position vectors there, that is just the vector that goes from the origin to a specific point. So, you know, a position vector for the point 1, 2, 3 is really just the vector 1, 2, 3. Yeah. So don't worry about that. Yeah, to make a direction vector using A and B, honestly, we could go either way. If we want to start at A and end at B, I think we'd go B minus A. So that would look like 4, 2, -1 minus, that's not a B. Okay, sorry. 4, 2, -1, and then 1, 2, 3. And if we subtract those, we'd have -3, 0, and 4. So that looks like a direction vector. And then in order to, that's step 1, and then step 2, write it in parametric vector form. There's our line, and our direction vector is the one that gets the parameter. Let's call it T. And we just choose either of the points, 1, 2, 3, because that's easier to write. And if we wanted to, we could go into Geogebra and show you this. Let's do it to make sure that we're not all over the place. Okay, ignore that. That's something else that we're going to do later. Okay, point A was 4, 2, -1, and point B was 1, 2, 3. We do direction vector, let's call it little d, equals B minus A. There's a vector, and if we wanted to, we could even change the position of this vector by going to its settings and say, hey, start at the point A so that that vector looks like it goes between the 2 points. Okay, great. But then in order to make the line, we could just do D times T to let us, that's the direction vector that we want to use, and then plus A gives us the line that we want. And, indeed, it goes through those 2 points exactly like we want it. Okay, example 1, done. Moving on to example, okay, there's the vector form and parametric form of a line. If you really want to copy that down, you can, but really it's just direction vector times T plus starting point, like we've discussed previously, and then those are the corresponding parametric equations that, again, we kind of talked about that stuff even on the first day. So I introduced that to you a little ahead of time. Now it's paying off. All right. Example number 2. Find both the vector form and the parametric equations of the line parallel to the direction vector 3i plus or minus j plus 2k and passing through the point blah, blah, blah. So again, we're just finding a line that goes through this point and is parallel to this direction vector, which means it's, all right. But again, we're coming up with a line, so we need a direction vector, we need a starting point. I'm not even going to write that down. We have them right now. The direction vector and oftentimes in our book, you might even see this thing that I've been drawing as just the general vector xyz. You'll also see it written as r of t because we are making a parametric equation. It's just that, yeah, it's a vector equation. But still, there's only one parameter. And yeah, we've got the direction vector 3, -1, and 2, no big deal, plus the starting point of -7, 2, and 5. That's the parametric vector form. And if you wanted to write it in parametric equations, you would just go along the components and say x is equal to 3t minus 7, y is equal to -t plus 2, and z is equal to 2t plus 5. No big deal there. Okay, example 2, done. Example number 3, determine the point of intersection of the line, blah, 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 with the 3 coordinate planes. Okay. In order to do that, we're going to make some things 0. So to intersect the YZ plane, we would set the x value equal to 0. So the x value of that line is 4 minus 3t. And if we solve for t, we'd have 4 equals 3t, and then 4/3 equals t. So this is where it would intersect the YZ plane. So if we, yeah, I'll say set x equals 0, that means this is the intersection YZ plane. Okay. And very similarly for the other ones, we would set the y value equal to 0, but 2 equals 0 does not have a solution. Which means that we wouldn't intersect the xz plane here because the y value is always 2. And then for the z, we could set z equal to 0 and I'd do the same thing. So we get 4t equals 1, and then t equals 1/4, and that is when it would intersect the xy plane. And sure, why don't we just make this real quick? Yeah. Let's get rid of the stuff that we had last time. Bye. Oh, here. Clear. Don't say it. All right. We have the line 4 minus 3t. Oh, I should make it a curve though, curve because that'll allow us now. No, I don't have to, I don't think. All right, let's do this. Sorry. 4 minus 3t, comma, 2 minus, and then minus 1 plus 4t. Okay. Can I do f of 4/3? Yes, dude. Nice. All right. What? I can't change the size of it. Anyways, that is where we intersect the YZ plane, just like we said. And T, nope, just kidding. F of 1/4, boom. This is where we intersect the XY plane. Yes. And then we never intersect the XZ plane because we're parallel to it the entire time. Nice. Okay. I'm satisfied with that one. Moving on. Example number 4. Determine the point of intersection of each of the following pairs of lines, if possible. Good grief. A lot to do here. The theory behind this, though, is we set the components equal to each other and then solve the system of equations. So, I don't know. Yeah, the idea is set components equal to each other, solve system. And that'll be using elimination, substitution, I don't know, Gaussian elimination, if you know how to put it into an augmented matrix. So the idea, I don't know, let's start off with A. Yeah, you'd set 2 plus 3u equal to 7 plus 2v, minus 1 minus u equals minus 3 minus v, and 2u equals 1 minus v. And so that is a system of equations with 2 unknowns and 3 equations. So there's a chance that we're able to make this work. And solving that using elimination or substitution, are there any good candidates? Yeah. Let's take this one and this one, and we're going to subtract one of those equations from the other. So let's do, yeah, I don't know. We'll just subtract the bottom one from the top one since it's already there. So the idea is we have -1. I'm going to make this a different color so it stands out. We are, it's fine to subtract equations from each other because I don't know, we've got equal things on each side. So subtracting means that we're changing the first equation by the same number. So we're doing a valid equation operation. So -1 minus 0 constants, that's fine. -u minus 2u would be minus 3u. -3 minus 1 would be -4, and then minus v plus v, because you're subtracting a negative, would just be 0. That was the idea. Get rid of v. Now we can add 4 to both sides to get 3, and add 3u to both sides to get 3u, and then we figure out that u is equal to 1. Once we figure that out, we can go back and substitute that into one of these equations. And as long as the values for u and v that we find here work for all three of the original equations, we're going to be great. I don't know why I pointed that towards v. It's going to go into u. So what we're going to get is 2 times 1 equals 1 minus v. And solving for v there, we would have negative 1. If v is negative 1, then it's like 1 plus 1, and we get 2. Okay. So there's our other one. And in order to check that, this is valid for all of them, I mean, we could just, plug in u and v to each one and make sure that we get the same thing on either side of the equation. Very similarly, we could plug them up into the vectors that we had before. So if we do that, I'll keep writing in blue. U is equal to 1. So this would be 3 times 1. This would be negative 1 times 1 or minus 1. And we'd throw a 1 in there. So the vector that we would get would be 2 plus 3 is 5. And we have negative 1 minus 1, which is negative 2, and 2 at the end. Then we'd be plugging in negative 1 everywhere where we see v. So we would have 7 minus 2, which is 5. Negative 3 plus 1, which is negative 2. And 1 minus negative 1, which is 2. And indeed, both of those are the same position vectors. They're the same point. And so that is the point of intersection for the first pair. For part A, there's our intersection. When you work through part B, and maybe you guys could come back and do this later, but I don't think we should do it now. Same kind of thing. You set the components equal to each other, then you solve the system. What will happen is that the u and v that you would find would work for 2 equations, but it wouldn't work for the third. And what that means is that part B is actually 2 skew lines that never intersect. They just go by past each other in 3-dimensional space. So yeah, that's something to look out for, but we're moving on. And if you guys want to do this later, go ahead. Here we go. Definition now for a plane with a known normal vector. And regrettably, I haven't shown you guys this yet, but now we get the chance to do it. This is something that is super cool. Probably the way that you're most comfortable seeing a plane equation is just the scalar equation down here, where you've got coefficients on x, y, and z, and it equals some constant. That's standard form. This one also works because this number d is actually the scaled version of some point in the plane. X0, Y0, and Z0 is just some point in the plane. And yeah, when you subtract by X0, Y0, and Z0 here, essentially what you're doing is shifting a plane that would have been out in space somewhere, but you're shifting it back so that the point X0, Y0, Z0 is functioning a lot like the origin. Because if you were going to put in the point X0, Y0, Z0 for X, Y, and Z, then you'd get a bunch of zeros there. So yeah, it's kind of like shifting a plane out there back down so that this point's functioning like the origin. But you might notice that we have a bunch of products and then add addition in between them. And that means that we can formulate this as a dot product. And so the cool thing about this is that planes are solutions to dot product equations. And specifically, we're looking at a normal vector being perpendicular to all the points in the plane. So I guess, yeah, let me label that real quick. I mean, this is the normal vector. And these are the points in the plane over here. Cool. So picture time. All right. We have a normal vector here, n, or whatever. I'm not going to change its color. Normal vector. And we have the plane in blue. This happens to be, yeah, the plane x plus 2y plus 3z equals 5 right now. And I can change any of these just by changing these sliders. One of the most interesting things to look at would be changing d, because when we change d, that means we're shifting the plane along the direction of the normal line. And if we make d equal to 0, ooh, so close. Kidding me. Okay. It means that the plane goes through the origin. And this is probably the easiest case to understand. Yeah, the idea here is that we've got a normal vector 1, 2, 3, and any point that is a solution to this dot product saying that some arbitrary point is perpendicular to our normal vector 1, 2, 3, then it's one of the points here in the blue plane. And I can drag this around, and everywhere you go, no matter what this point P is, right now it's close to 6, close to 1/2, and close to negative 1.5, but that can change. But the dot product that you would get always remained fixed, and it's always 0. I think that's super cool. So the plane is the solution set to this dot product equation. And yeah, earlier what I was saying is, if you shift that constant on the right-hand side, d, then you get a shifted plane. And now all of the points on this plane have a dot product of 5 with the normal vector. And that's the thing that stays constant. So the d that you have on the end is the constant dot product that you would get with the plane's normal vector with any point in the plane. I think that that's super cool. All right. Let's go ahead and go back here. And we'll put this into practice. Okay, so we are going to find a vector equation and scalar equation for the plane containing that point and having that normal vector. So first one I think would be the vector equation, because that's just what was introduced to us. So in this case, ABC is coming from the normal vector. So 2, -4, and 1, dotted with the points in our plane. -3, 1, 5 is one of the points. So all of the points, now we're, yeah, because that's a -3 and this is x minus x0, that turns into a +3. And then y minus 1 and z minus 5 means that we've incorporated that point. And essentially what we've done is, by this transformation, we've shifted everything down. We've done a translation such that -3, 1, 5 behaves like the origin. So if I was going to put -3, 1, and 5 in, I'd have the vector 0, 0, 0. And then this is equal to 0 because we want those things to be perpendicular. And then in order to get the scalar equation, we just take the dot product. So we'd have 2 times x plus 3 and -4 times y minus 1 and 1 times z minus 5 equals 0. And then we just collect like terms and such so that we'd have 2x, 2x plus 6 minus 4y plus 4 z minus 5 equals 0. So we'd have 2x minus 4y plus z equals 6 plus 4 is 10, minus 5 is 5, and then bring it over to the other hand side, it would be -5. So real quick, let's just open up a blank one and we'll do that again. Yeah, let's clear this one. Bye. We've got a point. Let's call it A. And it'll be -3, 1, 5. Boom. And a little vector n. That's our normal vector. 2, -4, 1. Awesome. And we are creating a scalar equation for the plane. That's what we did. So I'm just going to type in that scalar equation. 2x minus 4y plus z equals -5. And we're hoping, yes, that this plane is normal to the vector and it goes to the point. So boom. To review, we utilized this dot product to come up with the vector equation, and then we just took the dot product to come up with the scalar one. Moving on to example 6. Describe this plane as a 2-parameter set of points in R3. Okay. In this case, yeah, we're in a plane. You've got 2 degrees of freedom, 2 directions that you can go independently of one another, and the linear combinations of those 2 directions fill out all the points in a plane. So really what we're doing here is we're going to choose one of these variables to be like our basic variable, and 2 of them will be free variables, which yeah, basically just means we're going to solve this equation for one of the variables and then write the 3 parametric equations that way. The easiest one to solve for would be z. So how about we do that? Z would be equal to minus 2x. And actually, all right, let me leave some room. Z would be equal to 2x minus 4y. Nope, plus 4y. Just please. All right, I'm subtracting things over to the right-hand side. So they're going to change sign. Negative 2x plus 4y, and then minus 5 will just stay there. And then x can be x and y can be y. Those are our 2 degrees of freedom. And this thing is not showing up. I just noticed that. So hopefully that will show up soon. Yes. So there's a set of 3 equations. One of them solved for z in terms of x and y. But what we're allowed to do now is just substitute a parameter for x and y. And then we've got x equals t, y equals s, for lack of a better letter. And then z, I should have used w. I like w. Minus 2t plus 4s minus 5. There's a 2-parameter set of points in R3. And if you wanted to, you could turn that into parametric vector form and you'd have 2 direction vectors and 1 starting point. Super cool. Let's go to number 7. Number 7 is find an equation for the plane containing those 3 points. Boom. So planning ahead, we've got 3 points. We make 2 vectors in the plane. Using A, B, and C. Once we have those 2 vectors in the plane, then we take the cross product to get a vector that is perpendicular to both of those vectors that we made, and that will serve as our normal vector. So take cross product to find normal vector. And then create the plane based off of the normal vector and a point. Okay. Cool. Having done that and knowing that you guys can do those operations by hand if you need to, I'm going to take the liberty of just going to Geogebra so that we can see all this happening, and that I don't have to calculate things like a cross product. Sorry if that isn't giving you enough practice with calculating the cross product. A is -1, 2, 2. B is 2, 1, negative. Nope, just kidding. -1, 1. And C is 2, 2, 1. Boom. All right, so 3 points. We need to make 2 vectors. I don't know. Let's make them both point from A. So we'll go from A to B and then A to C. There actually is a vector command where you can just put in the start point and end point, but I kind of like to use the math. So let's make a vector u, little u, and all we'd have to do is do b minus a, since we've already got those points. Oh, I guess the vector in between 2 points, it is superior. I'll do that for this next one. V equals vector, start point A, end point C, boom. Because it already does the translation for you so that it's up between those 2. But I can just, again, move the position of this one so that we're in the right spot. Okay, so subtracting those points from one another gives you the correct vectors. And now we've got 2 vectors in the plane. Now the plan is to cross product those. So cross u, v, v, goodness. And again, that looks kind of weird. Let's move this vector to start at point A as well. I don't know. I like that a little better. Give it a different color. Cool. So that one is the cross product. That's our normal vector for the plane. So now what we can do is use the coordinates there and use one of these points to come up with, I mean, we would already be able to come up with the vector equation for the plane. Not too bad. The scalar version of it is going to be a little bit tiresome to do on GeoGebra, but maybe we can do it. Because I can't enter in like a vector x, y, z and just have it be a vector that I can do a dot product with. It doesn't work in the syntax. Because I would love to, I don't know, I don't know, can I? Let's try. But it's fine if I fail. So the idea here is we're going to make that other vector. Let me show you which one I'm talking about. We're going to make this vector that describes the points in the plane. And we're going to throw x, y, and z in there and see what happens. So x minus, let's use point A. So minus -1 is actually going to be +1. I'm just going to do that. And it's going to fail horribly. Y -2 and z -2 again. Oh, see, GeoGebra doesn't like that at all. I'd love to be able to do that. It just doesn't work. One of the things that we can do is come up with that scalar equation using, we've got 3x plus 9z equals, I guess this would be the dot product between our normal vector and A. So actually we can do that, I think. Let's do W dot A and see what we get. Yeah. Okay, actually that wasn't so bad. I should have just done that first. I shouldn't have tried to make the weird vector. So you can take the dot product between a vector and a point in GeoGebra, which is, I mean, just a different notation for kind of the same thing. But yeah, that gives us our D. And yeah, looks great. We made the plane that we set out to make. Okay. Moving on. Find the point of intersection between the line R of t equals that and the plane blah. Easiest way to do this would just be to put the components of the line into the plane and solve for the value of t where the line intersects the plane. So we would be solving 4 times 2 minus 3t minus y, which is 1 plus 4t plus 2 times minus 3 minus t, and that equals 5. And then we continue to go. So 8 minus 12t minus 1 minus 4t plus, nope, just kidding, minus 6 minus 2t equals 5. Combining like terms, we've got minus 12t, minus 4t, and minus 2t. So minus 18t. And then we've got 8 minus 1 minus 6. So 1 over here equals 5. Then if we subtract 1 from both sides, we get minus 18t equals 4. And then t equals negative 4/18, or, oh my gosh. I don't need to simplify this fraction, but I felt compelled to. So again, I didn't make the GeoGebra thing beforehand on this one. What am I doing? Let's clear this. Don't save. And we're gonna type in the line just to make sure that we got things right. 1 plus 4t. And minus 3 minus t. So there's a line. Plane that we're interested in is 4x minus y plus 2z equals 5. Boom. And then the point of their intersection, I'm just going to cheat, intersect, so I don't have to type in the point. Or actually, just kidding, I'm going to do it that way. The way that we do this, we found out t was equal to negative 2/9. We can go to f of negative 2/9 and get that point. We got it. I'm not going to cheat. We've got it. Okay. So we just plug the x, y, and z components of that vector, the line's vector equation, into the plane's scalar equation, solve for t, no big deal. Next one. These last three are kind of doozies. And we're running low. Oh my gosh, we're out of time. Example number 9, find parametric equations formed by the intersection of these two planes. One of the ways that you will see that's probably the easiest way will be in linear algebra. And what we'll do is take the scalar equations for these two planes and put them into an array called a matrix. And we will do row operations on them so that we make the front part of this matrix look like 1, 0, 0, 1. And that corresponds to having the first equation solve for x, and then we'd have 2/3 z equals negative 7/3, and we'd have 0x plus 1y minus 5/3 z equals negative 14/3. So essentially what this is just a nice way to do solving by elimination. And that gives us this system here. When we solve for x, y, and z, z is our free variable. It's the one that we just let be z, or t in this case. And then x was equal to negative 2/3 minus 7/3, blah, 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 blah. And that is a straightforward way to just work with the scalar equations, do elimination, and you come up with an equation such that you've solved for x in terms of z, you solve for y in terms of z, and z is just itself, so that you're able to get a direction vector and starting point, no problem. The linear algebra way here seems a little bit more straightforward, at least in terms of calculating it kind of by hand and having a nice set of steps to go through. And if you've already taken a class where you've worked with matrices, feel free to use row operations to solve a system of equations. That's really all you're doing there. In our context, though, we can make use of the fact that we've learned about the cross product. Each of these planes has a normal vector, which we can read off. And the idea will be if we use the two normal vectors to each of these planes, and then we find a third vector that's perpendicular to the normal vectors, the direction that is perpendicular to the normal vectors is actually going to be the direction vector for the line. Let's go ahead and look at that on GeoGebra. So here are our two planes given by these scalar equations. We're trying to find the equation of the line between them. First thing to do, two normal vectors. And those are, again, just the coefficients on our scalar equations. And then we take the cross product of those two normal vectors to get us the direction of the line. Since those are both orthogonal to the planes, the thing that's orthogonal to the orthogonal things is actually parallel to both planes and is going to go down the line of their intersection. And since we have a direction vector, the only thing that we would need now is a starting point. In order to solve for a single point, probably you would want to throw in another plane just so that those three planes intersect at one point. Here, I just chose the plane z equals 0, which would just, make the z coordinate equal to 0. And if you threw that into the system that we started off with, just make z equals 0, then you're in a system of two equations with two unknowns. X and y would be the only ones left. And you can do a 2x2 system using substitution or elimination. So you would be able to get this point at the intersection just by setting z to 0 and solving. And then utilizing this point and the direction vector, you can make the line. The direction vector gets the parameter t. In this case, it's showing up as lambda, but I actually entered it as t. Let me see if I can duplicate the input. Nope. Great. The way that I input this line was t times the direction vector, in this case was w, and then plus a. I promise I entered it like that, and then it changes. Anyways, cool. All right, so that's example number 9. Sorry. Example number 10. Again, we're just trying to get kind of the big idea here. Find the shortest distance between a point and a plane. So this point is not on the plane. We're trying to find the shortest distance. The idea here will be one, create a vector from a point in the plane to A. So take any point in the plane, make a vector to A. And once we have that, we will be able to project that vector onto the normal vector. Okay, so that's the plan. Let's see how it looks. All right, so A is our point 3, 1, -2. B is a point in the plane and that I can literally drag around wherever I want to. So that's cool. And if you wanted to find a point in the plane, really all you have to do is find something that makes this true. So to get 2 on the right hand side, you could just make x equal to 1 and then y and z equal to 0 as a, for instance. It's a pretty easy way to just find a point. But yeah, once you found a point, you make a vector between that point and A. So boom. And you can do that just by subtracting the 2 points. Our normal vector is 2, -3, 6. And what we can do is project this vector BA onto the normal vector, like so. So projection. And that gives us this vector. So this vector is the one that is the shortest distance to travel between the plane and this point. I think I translated that and changed the direction just to show you that, like, yeah, you can start at this point and get to the plane, and we're traveling in a direction that is orthogonal to the plane, so it's the shortest distance. And the length of that is about 1.57. You need a square root in order to actually get the exact answer. But that's just distance formula. You guys know how to do that. So yeah, you can find the shortest distance. The distance would be just the magnitude of that vector, the projection onto the normal vector. Okay, last one. Find the shortest distance D between the two skew lines R and S here. What's the idea here? So two skew lines mean that they never intersect and they're just going off in different directions in 3D space. What do we know? When we have two skew lines, we have two direction vectors. That's a good thing. And the shortest distance between those two lines is going to be perpendicular to both of those directions. So cross product. We're going to take the cross product between the two direction vectors. And then we're going to project a vector that starts at one line and ends at the other one, just like we had a vector that started on the plane and ends at the point. We're going to have a point on one line and a point on the other line, and we're going to project that vector onto the normal vector again. So this is our last one. Okay. Two skew lines in space. A and B are given to us there because these are the coordinates that don't have a variable or a parameter with them. So 2, 3, 2, and 0, 4, 2 are the 2 points, A and B, that are easiest to use. Did I type that incorrectly? Oh, yeah, it's the first one. That's just 2V. Okay, we're good. So R and S are fine. They each have two direction vectors, first direction vector, second direction vector. Take the cross product, we get a normal vector, and this normal vector is the right direction to travel to get the shortest distance. And so again, we create this vector U between A and B, and what we do is we project that vector U onto the normal vector. And this is what the projection would look like. And the length of this projection vector is the distance. So, I mean, I guess I didn't even do that on this yet. Projection of N, or sorry, of U onto N. All right, it's about 0.9 is the distance. And that distance would happen, well, I don't know, when you're looking straight down on it, it would happen at some point around here. But yeah, in order to find those, we need to do a little bit more digging. But that actually wasn't part of this problem. So we'll save that for later, some other time, if we wanted to find the actual points that would connect those. But Yeah, the length of this projection vector is about 0.9, and that answers the shortest distance between the two skew lines. So again, in summary, two direction vectors of the lines, cross product, then project any vector that goes between one line and the other onto the normal vector to get this, and that's the distance. Cool. All right, well, the homework on that is a lot of true and false questions that we'll be able to discuss on homework day. I know this is already too long, so I'll say see you later. Thank you guys for being patient and watching 2 video lectures in a row. All right, see you tomorrow. All right, bye.